Alright, for our third and final video in this lesson, I'm going to cut it a little shorter. I had some initial ambitions of covering more models. I'm just going to jump to one, the SEIR model, which we had talked about a little last time. It was one of the last slides of the previous lesson. Actually, I had the last slide was an SEIRS model, the last S meaning that you could lose immunity. And with COVID-19, we don't know, but for a lot of similar viruses, you do lose immunity eventually. But we're going to focus on this model, which will be fine for the time scale that we're thinking about, this current pandemic. And so the idea is we're adding an extra compartment or category called exposed. So this is useful for describing diseases like COVID-19, where you can be exposed to somebody who's infected and you don't show any symptoms and you're not necessarily contagious for a bit, but you're definitely carrying it. And so there's this compartment, this in-between compartment between susceptible and infected. So now we have four compartments: susceptible, and then a rate at which you become exposed, and a rate at which the exposed become infected, and then a rate at which the infected become recovered. And we'll see a couple more sophisticated versions of this in this little video. So here are the equations, and I've highlighted in green the ones that are different over the SIR model. We had left off last time looking at some graphs and consequences of the SIR model, susceptible, infected, recovered. And now we're adding this E for exposed. And so it's a little bit different. Remember, these primes just mean change. So this is the change in the number of susceptibles, the change in the number of exposed, the change in the number of infecteds, and the change in the number of recovereds. So susceptibles decrease, their change is negative. And where do they go? Well, they become exposed. So that increases the number of exposed. What's decreasing the number of exposed is some rate at which they become infected. So as exposed folks become infected, they move from one compartment to the next. That's what these terms are saying in the equations. And then folks that are infected recover at the same rate as before. And the rate at which you're losing infecteds is the rate at which you're accumulating recovereds. And in this model, once you're recovered, you're not susceptible again. So just a couple of graphs here. So there's now 4 curves instead of 3 on our SIR model. We would have curves for susceptible, infected, and recovered. But now we also have a curve for exposed. And there's a bit of a lag time there. Notice that the yellow curve, which is the exposed curve, peaks before the infected curve. It leads the curve, right? Folks have to be exposed before they're infected. So this curve leads the infected, right? Then kind of just jumping a little quickly here, I found a bunch of sites that were just doing some really great programming and creating more sophisticated models. One had made another compartment for dead, morbid compartment, of course. And then you can just run simulations. In this particular page, use Python. And now we have a yellow curve that's exposed, a red curve that's infected, and then a black curve, which is those that don't recover, that pass away. And it's also lagging, right? If you kind of notice where these things are, exposed peaks, infected peaks, and then over here, this is flatlining, some total number of losses. Basically after everyone's become susceptible, right? And people have recovered, there's some who didn't make it. Now this process of adding more compartments, of not just having 4, but maybe having a number of other compartments, is actively being done in research right now. It was done not very long ago based on data coming out of China in February. And I just want to kind of wrap up with this because I want you to see how this is being used in action. Here's a quote from the paper, and notice that you're already able to understand some of this, even though it's a research level paper appearing in a journal about infectious diseases. So they say we adopt a susceptible, exposed, infectious, removed framework, SEIR, the total population size N, and 2 extra classes, so 2 more compartments. They use D to mimic public perception of risk regarding the number of severe and critical cases and deaths, and C, the number of cumulative cases reported or not. So they add a couple compartments, and their equations are a bit more intimidating than ours. But there's your S prime, E prime, I prime, R prime. They also have some other categories here. This particular paper, they're also looking at how the transmission rate changes with different government action and public perception. So they're really trying to figure out how things change if different personal or government mandated measures are put into place. Based on the data coming out of China, they were trying to come up with some scenarios as to what was likely to happen. If you look at the paper, which is linked right here, it talks about the time, the data they were looking at. There were only about 70,000 cases in China. This was quite a while ago, and kind of interesting to think about that. And actually, yeah, I just want to show you a couple graphs in that paper. So this is the kind of stuff that those equations can generate. And without getting too into this or worrying about it, basically what we have here, we have this dotted line. This is daily new infections. Remember, I told you that daily new infections, that's one of those things that peaks, not cumulative cases, daily new. And this is that tall peak, right? And what do they have here? They study a couple of things in this paper. One of them is like individual reactions. During a pandemic or an epidemic, people might limit their exposure to other people. They might self-isolate voluntarily, and that certainly limits things. But then they also study, they model anyway, possible government interventions on the SEIR model, and they have this right here. And so this is hopeful. What they're trying to do is to figure out, based on the data, what might happen if governments and communities impose various mandates on the public. And it's suggesting, like we've been seeing, that it will limit some of those infections. Again, naive. This is assuming that nobody cares at all. We just go about our actions. So the reason people use mathematics sometimes, actually most of the time really, is to try to describe something and to try to make a prediction. Those equations that we're seeing can be put into code, programming language, simulations can be run, all these letters like beta and mu and whatnot, those can be estimated based on data coming out of various countries, and they can try to figure out what's likely to happen. Now, they're almost certainly going to be wrong. That's just the nature of things. Um, but it's better than nothing. And you can only imagine, what it's like right now. I have no idea. For those epidemiologists that are trying to figure out how long we have to do this, recognizing that it's causing severe consequences for the economy, and for a lot of people who don't have a lot of savings, who aren't getting paid right now. How long do we do this? What's the balance? Of course, mathematics isn't going to provide the answer, but it might provide part of the information or part of the idea. Okay, kind of looking forward a little bit. Next week, week 5, is the exam. And I'm not going to produce any new content on TopHat, so we'll kind of take the week off, if you will. You can study, make your notes. I'd recommend having notes and outlines for the test, just so that you don't have to go, fiddling around the internet, looking up things in TopHat or whatever. Try to organize those questions and understand what it's about. Again, you'll have 24 hours to work on that exam, depending on when you wake up. But, definitely at least 12 hours if you wake up by noon. So I hope you're well. I hope you're healthy. I hope you're safe. I miss all of you. is another use of Bitmojis by a middle-aged guy. Probably shouldn't be using them. Take care. I'll see you next time.